Bill Buttlar.
Thanks for being in. Good afternoon, ladies and gentlemen. Thanks for sticking with us on this fun and first research day. And it's my real pleasure to talk about a third and very important pillar in Dean LeBeau's vision for kind of reorganizing the college in these future directions. And I'm just really happy to talk to you about sustainable pavements. So we'll go back to the first slide and get ready to go. And the topic is from rubbish to roads. I've invited some of my graduate students and visitors to mainly just as an exercise in humility, but just to provide some visual aids for the talk. And so let's get right into it. So sustainability. I've never thought of myself as an environmentalist, but in some sense we all are. We love the environment, and it's amazing. And I just revel in it. And I have the opportunity to travel all over the world. For some reason, you get a little older, you get a few gray hairs, and everybody wants to hear about what's going on in your lab. And so I visited China a lot. It's just in South Africa, and I've got some pictures up here, just taken with my smartphone. Just the amazing things we see in our environment, and it is motivating to do research that helps protect the environment and sustain it and make it more resilient. And so it's a very, very motivating topic. We want to minimize this, and so civil engineers do help build the environment out. It's the built environment that we're trying to get people from point A to point B. It's for your health, it's for your comfort, it's for prosperity and enterprise. But if you think about it, over the last 100 years, we've cut some pretty big quarries. So this is a quarrying operation. This is Interstate 80 in Chicagoland, and you don't really realize it when you're on I-80, but you're over a 600-foot hole in the ground. When you fly into O'Hara or Midway, you see these quarries, and they're kind of scars on the landscape. Eventually, we can fill them back up, or we can feed them with springs and reclaim them, build on top of them. But while we build out the environment, it can be a pretty disruptive enterprise. And so my research over the last 20 years has really gotten more and more and more into trying to minimize these things, and especially things like this. So we've spent a lot of time looking at scrap tires and thinking about how we can balance the use of tires on vehicles and maybe get them back into the road. Sometimes they're used for fuel, but I mean the carbon release and the pollution from that is not a great use. So maybe we could use every little bit of the piece of the tire that's coming out. And so actually this field, civil engineering, road materials, has led the world in recycling in terms of tonnage, in terms of percentage, and it's going great. When I got into the research realm in about the 1990s, things were going well with some early recycling. The main thing was just taking old asphalt and putting it into new asphalt. We call that reclaimed asphalt pavement, or RAP. And so you can see some of that road reclamation. So Bainam here is kind of show you that we start with just the broken up pavement, and it's not suitable to mix with the new materials, and so we have to process, sort, and get this ready to be used in a more highly engineered way so that we can control the use. We also have used byproducts like steel slag, and it's great because it's very, very high friction, so we can use that for meeting our skid resistance requirements for interstates, high speeds, turns, and so you can just see an example of how steel slag has been used as an input to asphalt. So I get really excited about asphalt because it's a moldable and remoldable and flexible material, and it's you can just recycle and recycle it, and you can float it over old asphalt, concrete. And so we've spent a lot of time trying to think about more ways to get more of these materials in. And one of the big challenges is that it sometimes is too brittle. So the asphalt does get hardened by UV radiation, by oxygen, just like a polymer would. And I also noticed that the tests were being developed were kind of the wrong tests for recycling. They were the right tests for more performance and for more scientific measurements, viscoelasticity, fatigue, but more on the component materials, the glue or the asphalt. Well, that's only 5% of the weight of the material, and we really need to test this whole composite heterogeneous material. I was coming from the structures and mechanics field, and so I had a mechanical model of how we would get to higher recycling and new materials. And maybe lessons for the Liberty ships. So in World War II, these Liberty ships were made with just the standard metals, standard welding techniques. And as they went north into the cold ocean water, they almost all just one after the other cracked down the middle. And when the fracture mechanics people just launched the modern field of fracture mechanics, and they learned that, well, the welds were kind of junk welds. They were filling them, and they should have just been solid welds. And the metal was not really designed for cold temperature. And so I was thinking about how fracture mechanics could be used to solve some of these problems when we have a little bit more brittle material. And so we developed a compact fracture test. And to go from research to practice, you have to commercialize it. So we worked with a company to commercialize these machines, and now they're all over the world. We had to standardize those, and so the next process is having something like ASTM International that would standardize the test so everybody can run it the same way. And then we had to hit it hard with analytical models, computational models, supercomputing. And for some reason, this test was called the Pac-Man test. I'm not sure why, but it's really caught on, and that was kind of launched us into the modern design. Now we had a new tool in our toolkit to try to look at new materials and to get them in higher quantities as well. And so the next one is ground tire rubber. And rather than have tires in the landfill where they fill up with water, mosquitoes come in, causes malaria. I mean, just as a visual effect. Come out this way. Meet my son, Brandon.
Social services on its way.
Yeah, these are filled with all kinds of good things. Why would you want to burn? You grind this up and you've got fiber, you've got nylon, you've got metal, you've got, of course, the natural rubber that's in here that can be used in all sorts of processes. And so recyclers have figured out how to cryogenically freeze and crush or grind this material, ambient grind, and it keeps getting finer and finer. We first started engineering it. It was large pieces. We were trying to replace the rock and the asphalt concrete, big, quarter-inch pieces. Now it's ground down to like 40 pieces per inch and 40 mesh. And you can see the nylon in there. There's a little bit of metal. And there's this new process of engineered crumb rubber where you also graft chemicals on the surface that impart all sorts of advantageous properties to the asphalt. You also have to get out into the field. So here's a couple of my students out with me. They only close O'Hara Airport down at night for construction. So every night we're kind of ripping out the old pavement, 9 right, busiest runway in the world, and putting in these advanced designs and advanced materials. And so we have major cost savings, increased performance. This is one of those recycled materials that doesn't just save you money and cut down on new material use, but it actually improves the performance, and that's what our lab is really, really honing in on. Roofing shingles. Next example, Hamid. He's holding up some ground-up roofing shingles. This was a tough challenge, and our lab has done more of this than any lab in the world. How to go from waste, especially tear-off shingles, 10 million tons a year. There's about 1 million tons of just break-off new shingles that are broken during manufacture. 11 million tons of this stuff, but it's rich in asphalt. It has 5 times the asphalt content of the old asphalt. So it's an asphalt-rich material, which is the most expensive part of asphalt. But we've had to really soften up the asphalt by using rejuvenator oils and other very, very soft base binders, run them through the fracture test, and we've been able to push up recycling rates in Chicago up to 70% recycling. And there were a lot of critics. In fact, Federal Highway came out and they're like, well, your state is recycling way more than the federal average, and we really want to know, are you doing this right? So I had to prove to them that. Just released this week, Sustainable Infrastructure Materials and Systems, and this journal gets about 1 million hits a month, and the way these open access journals work is we pay a small fee. Of course, when you run the special issue, they waive the fee, so yay. But for a small fee, our colleagues will put a paper in this, and it's just open from here to eternity, and it should get a lot of impact. So we're excited about that. So, where have we come in the last 20 years? Well, almost 10 million tires were used last year in pavements, but we can probably number being put into research. So for a fraction of a percent of the savings in recycling, I mean, that's all the research that you need to have a huge return on investment. So, hey, what about the next best things? Big things. One is Aoxidor. So at the University of Illinois, we had developed this 3-part condensation reaction where we could basically put antioxidant components in asphalt in a stable way. And we applied for a patent in 2010. I was a year into working here, and about a year ago, I got an email, hey, this patent was granted. And so now we're trying to figure out how to work this into our current research with all these recycled materials to slow down the oxidative hardening or just the hardening rate of asphalt by building in antioxidants in that. So that will be extended here, and that will allow increased recycling with reduced cracking and reduced cost. And so the last piece that I want to talk about is the intelligent infrastructure research. And so we're going to continue out into smart roads and smart cities, and we'll continue using our fracture test. I never did wave over to the DCT fracture test, so thanks Loretto. Loretto comes from Chile. I met her when I was helping solve the reflective cracking problem in her country, and she got interested in the lab and is leading our performance testing group, and is definitely integrated with the Smart Cities group. What we're working on is a holistic concept of active digital asset management, where we have cars that are autonomous, they're talking to one another, they're collecting a huge volume of data. They're also assessing the roads, or could be used to do that. We have smart instruments that connect to the cloud for cloud computing, fixed sensors. It's really just an integrated big data system, or data science system, depending on where you're trying to get funding. And we connect things like, this looks like a garage door opener. We had a poster. This is actually a molecular sensor. Most people use it to take a look and make sure that they've got the right prescription medicine, or to make sure when they go to the grocery store they're buying fresh fruit and not spoiled fruit. But we figured out how to use this to fingerprint asphalt. So in a smart city application, this would just connect to the cloud, and you can do very rapid assessments of asphalt age or asphalt quality. Nano modification of asphalt. We have a couple of new partners. Matt Mashman, I think, is here, and mechanical engineering and Wingo. It's a company right here in Columbia. They did a search, Smart Asphalt USA, and then 2 miles away is our lab, and we had just set it up, and they came and talked to us. They were looking for a research partner. So they're using carbon nanotubes and other nanomaterials to modify asphalt. They can change the surface color of asphalt and asphalt roofing shingles and roads. They can make digital displays out of surfaces like roads. And, but they're trying to figure out how to integrate that into asphalt so that it performs well and it's durable. And so we're just launching a whole suite of research with them, and that can tie into smart cities. You can detect cracks, you can harvest energy, you can use energy to heal pavement, you can energize cars from the road. Those are all the different things that we're looking to do. And even partnering with the City of Columbia, Kansas City, MoDOT, National City Lab to get this technology out to the masses. So this is the direction. We have millions of dollars of NSF proposals either submitted or in the works to drive this out nationally as well. So we're kind of up against time, and so we're going to stick around for refreshments. I invite you to visit my lab as well and visit with all of our keynote speakers afterwards. But I want to wish you safe travels, hopefully on smooth, green, or blackish asphalt roads. Thanks to the college for putting together this great research day, and visit the Missouri Asphalt Pavement and Innovation Lab. There's our brand new logo. Thanks a lot for your time.